We're going to use inequalities when we compare quantities that are unequal. So if two numbers aren't equal, like a and b, as I'm calling them here, the two possibilities are either a is less than b, using this symbol, or a is greater than b. The symbol opens up to the larger value. A useful way to look at this is by focusing on the number line. Here I'm going to mark two locations, x and y. So clearly x and y are not equal, but you can still compare them using one of these two symbols. If we move along the number line in this direction, we're going from smaller to larger values. So on a number line, since x appears before y, we would say that x is less than y. So what I'm going to do is write out that x is less than y. I can actually visualize it on the number line. Also, if you move on the number line in the opposite direction, we're going from larger to smaller values. So this is a point of confusion, but you could equally say y is greater than x. So what I have written here are both correct. You could actually use both of the symbols that we just introduced to describe what's happening on this number line, and either is completely acceptable. Either x is less than y, or y is greater than x. So let's use these in example 1, where I have two values, and I want to compare them using less than or greater than. Starting with 5 and 1, I know clearly 5 is a bigger number than 1. You could draw on a number line. 5 would be over here, 1 would be over here. So definitely the answer is going to be 5 is greater than 1. And it doesn't matter how large the values are. Again, here we have 28 and 496. Clearly you get to 28 before you get to 496. So in this case, I'll say 28 is less than 496. Maybe if you throw in some negative numbers and a positive one, that might be a point of confusion, but negative is going in this direction, the positives are going in this direction. Clearly 104 is greater than negative 8, or said another way, negative 8 is less than 104. If both of the numbers are negative, so as you're moving in this direction, you would get to negative 12 before you get to negative 50. Therefore, negative 12 is greater than negative 50. Then maybe just a couple. Here we have decimals and fractions. So this is 0.002, and that's 0.01. Even though the 2 is larger than the 1 appears earlier in the decimal expansion than the 2. And for this reason, I know that 0.01 is greater than 0.002. And then lastly, here we have a couple of fractions. I think a good way to go about this is you can even type it into your calculator, and instead of use fractions, compare it as decimals. So if I do that, type in 2/3 and I get 0.6 repeating forever. And then for 3/4, I got 0.75. Okay, so clearly 2/3 is less than 3/4, or you could even say 3/4 is greater than 2/3. Now that we have an understanding of what less than and greater than mean, I want to introduce an example that has a variable in it. I want to solve this inequality by drawing my answers on the number line. I want to mark all of the numbers x, where x is greater than. In this case, this symbol means equal to 2. So same idea, greater than, but we're going to allow an equals in here as well. For something this simple, there's an easy approach to take. I can draw the number 2 on the number line, so maybe I'll put that right here. And I want to figure out all numbers x that are greater than or equal to 2. Since I have an equal sign, I'm going to shade in a circle at 2, and that indicates that I can include 2 in my answer. So off to the side here, in place of x, I'll put 2. Is it true that 2 is greater than or equal to 2? And the answer is yes. Now, if I want to get the rest of the numbers that make this thing a true statement, there's only two possibilities. It's going to be all of the numbers on this side, or all of the numbers on this side. So I'm going to just choose a couple values, like maybe 3, 4, and 5, plug them in place of x, and see if they make this thing a true statement. So let's start with 3. Does 3 in place of x make this true? Well, 3 isn't equal to 2, but it's certainly greater than 2, so yeah, that's good. So you can fill in this spot. Same thing goes for 4 and 5. But not only those points, but everything in between those values as well. The answer to this problem is going to be everything that is to the right of 2. All of those numbers make this thing a true statement. Now, if for some reason you pick things on the other side, like maybe you're going to check 1, 0, -1, and so on, do those make the inequality true? So I'll plug them in off to the left here. Is 1 greater than or equal to 2? And the answer is no. So we would not want to shade that number. And the same thing goes for 0 and for -1. Clearly, these both are false. So we don't mark those down on this side of the number line. The takeaway is mark 2. The equal signs mean I shade this in. And greater than meant we're going on the right side of the number, not the left side. Let's compare that to example 3. So in example 3, same idea. I want to shade all the numbers on this line that make this a true statement, and I'm going to start by putting 5 on my number line. Doesn't really matter where that goes. Maybe I'll place that over here. This is 5. In this instance, can you use the number 5 in this inequality? That is it true that 5 is less than 5? And the answer is no, that's false. For this reason, I'm going to put an open circle at 5. That's our way of saying 5 is the barrier, I'm just not including it. What we have to decide is, are we going to shade all of the numbers to the left of it or to the right of it? There's only 2 possibilities. So let's see, you could check numbers like 6, 7, or 8, and maybe 4, 3, 2, 1, and so on. And just ask yourself, like, which of these numbers make the above inequality true? If you were to start with, let's say, 6, 7, and 8, I'll plug those in. Is 6 less than 5? Again, no, that's not true. And we could try it for 7 and for 8. And in fact, these are all false. None of these work. So I don't want to shade in this stuff over here. But if we try 4, 3, 2, and 1, so I'll choose 4. Is 4 less than 5? Yes, that's true. Same thing goes for 3, and for 2, and for 1. These are all true. So that means I'm not including 5, so I'm just putting that open circle there, but I am shading everything that goes to the left. So the takeaway from example 2 and example 3 is that if you see greater than a number, we go to the right. If you see less than a number, we go to the left. For example 4, same idea as the previous 2 examples. I want to find all of the numbers that make this thing a true statement, and then I'll shade them on this number line given below. But there's a problem. The issue is, it's not just x is less than 7. That would be very easy. You just go to 7 and then take everything that's to the left of it. The difference here is we have this 2x minus 3 is less than 7. But luckily, we have this above rule that I wrote here where I can in some sense treat this as an equal sign and solve for x. And then once I simplify it, it'll be easy to see what all the answers are. There's one exception to this rule, and we'll check that out in the next example. But if I look at this problem, my goal is to isolate x. I see I have a 3 here that I can add to both sides and then divide both sides by 2, giving me x by itself. But let's go through that carefully. I'm going to start by adding 3 to both sides of this inequality, just like I would an equation. It gives me 2x on the left and 10 on the right. And furthermore, you still get less than. The inequality is still true. If this side is less than this side, and they both increase by the same amount, the result here has to still be less than the result here. So I'm almost done. I want to get x by itself. I'm going to divide both sides by 2. So maybe I'll use a different color for that, but I want to divide the left by 2, and therefore I'm going to divide the right by 2. When I do this, on the left I get just x, which is perfect, And on the right, I get 10 over 2, which is 5. And this is my answer in simplified form. It's very easy to see what the answer to this problem is. As we just previously discussed, you would go to 5. I'll put an open circle there. Less than means I shade to the left. So maybe just to go through it really quickly again, to deal with this inequality, we're basically solving for x. And since I added the same amount to both sides, the inequality holds true. And here, this side was less than this side. If you divide them both by 2, you should still have less than at the very end of the problem. And for example 5, same idea. Here we have this inequality, and I want to graph the answers on a number line. But there's this one thing that can happen if you ever multiply or divide both sides of an inequality by a negative number. So let's see what happens through this process here. I'm going to take this inequality, and I want to get the x by itself, so I can first subtract 5 from both sides. So there's no problems there. If this side is less than this side, and you decrease them both by 5, the result is still less than. That is, negative x is still less than, in this case, 1. Perfect. But something weird happens here. I want to divide by negative 1. By doing this, it'll cancel the negative in front of x. That means I'm dividing both sides by negative 1. And when I do this, I do get x, because negative over negative is a positive, and just leaving me with x. And on the right, I get negative 1, because 1 divided by negative 1 is negative 1. But the thing that happens here is the direction of the inequality changes from a less than to a greater than. And that's what this rule is saying up here. Anytime that you multiply, or in this case, divide both sides of an inequality by a negative number, this thing will change from a less than to a greater than, or vice versa. If this had been greater than, it would go to less than. So at this point, I can now read my answer off of this inequality. I'm going to put negative 1 on the number line. That's over here. I don't have an equal sign, so I'll put an open circle. And x greater than negative 1 means I'm moving to the right, which this is the answer.